This is lesson 15, entropy. So, a spontaneous process is one that proceeds without any outside interference. Think back to electrochemistry and how if E cell was greater than 0, it was spontaneous, meaning it just occurred. Okay? And so, if we look at this picture, okay, we have two gases. We have gas A, we have an empty flask A, and we have gas B. Okay, and you can see the stopcock is closed between here, so the gases cannot go back and forth. But if you open the stopcock, what's going to happen is that gas B is going to gradually diffuse into flask A, because remember, gases expand to fill their containers. So this process going forward is spontaneous. However, it's very unlikely that all of gas B would spontaneously just go back into its container and return to how it started. So the backward or the reverse reaction is not spontaneous. Just because a reaction is spontaneous, however, does not mean that it's fast. So it could actually take hours for this gas to equalize between the two containers. So just because it's spontaneous does not mean it's fast. So entropy is a measure of the randomness in a system. So entropy has the symbol S, and if we're measuring the change in entropy, we're going to subtract the randomness at the end of our reaction minus the randomness in the beginning of our reaction. And the units for entropy are joules per Kelvin mole. So here's a picture of entropy. And you might notice that there's things in life that just happen. It just seems like no matter what you do, you cannot get things to stay ordered. For example, in your room, okay? And the randomness of your room always is increasing. It always wants to increase. And what is actually happening when you clean your room, you are trying to decrease the entropy of the universe. And in fact, the universe actually wants to be random. So the next time that your mom and dad asks you to clean your room, you can tell them, I'm sorry, but the universe just wants my room to be random because it's entropically favored. So the second law of thermodynamics says that the entropy of the universe increases in any spontaneous process. So again, next time your room is really messy and someone asks you to clean it, you can just cite the second law of thermodynamics. So there's three types of motion in molecules. So the first type of motion is called translational, when the whole molecule moves in one direction. That's translational. So for example, if my mouse is a molecule and it's moving across the screen, that would be translational motion. The second type of motion is vibrational motion, and vibrational motion occurs when the atoms in the molecule move away and towards one another. So if you look at this water molecule down here, you can have vibrational movement because the hydrogen and oxygen bonds here can vibrate back and forth, or the hydrogens can vibrate together, or one can go up while one goes down, and vice versa. The last type of motion in molecules is rotational motion, where the molecule is actually spinning. So, entropy actually can increase in many, many different ways. So the first thing that you can do is increase the volume of your container. If you increase the volume of your container, the gases that are in your container can now expand, and so they can become more random. The second thing you can do to increase entropy is increase the temperature, because all of those movements of the molecules will increase if you increase the temperature. Because the particles will all speed up super fast, so they'll become more random. And you can also increase the number of molecules that make up the system. So if you add more molecules, you are going to increase the randomness. So entropy will increase. Entropy will increase therefore when gases form from solids or liquids, because gases are more random, they move faster, and they can spread apart. If you form liquids or solutions from solids, again, you're increasing the randomness because you're dissolving a solid and you're allowing it to move faster. If you increase the number of gas molecules during a reaction, your entropy will increase. So if you have 2 gas molecules going to form 4 gas molecules, then your entropy is increasing. So your entropy is increasing in all these situations because your randomness is increasing. The third law of thermodynamics states that if you were able to reach absolute zero, 0 kelvins, the entropy of that pure crystalline substance would be 0. Because if you think about this, if your temperature is absolute 0, where all motion stops, you no longer have any randomness. Everything would be highly ordered in a crystalline substance. So how do we find entropy? Well, it was really easy to find enthalpy using calorimetry. It's much more difficult to measure entropy. So to do this, we're going to use standard molar entropies, which are very similar to standard enthalpies of formation. So standard molar entropies are the molar entropies for substances in their standard states at 1 atmosphere. And this formula should look familiar because it's the same thing as Hess's law, except for now to find the change in entropy, you are going to subtract the sum of the moles times the entropy of the products minus the sum of the moles times the entropy of the reactants. So what about these standard entropies for substances? So unlike standard enthalpies of formation, the standard entropy of a substance and even a pure element are not equal to 0 because they all have some type of randomness. The entropies of gases are always going to be greater than the liquids or solids because gases are more random. And entropy will always increase with increasing molar mass because the more mass you have, the more random you can be. Remember all those motions, vibrational, translational, rotational. So if you have molecules with greater molar mass, they have more randomness. They also increase with the number of atoms in the formula because the more atoms you have, again, the more random you can be. So we also are able to calculate the entropy change in surroundings. So the enthalpy change or entropy change in the surroundings is going to be equal to the negative of the enthalpy change of the system over temperature. And this formula is not used very often, but every once in a while it pops up as a question on the AP exam. So, exothermic reactions and entropy. Exothermic reactions are actually more common than endothermic reactions because a negative delta H, meaning energy is released, leads to an increase in entropy or randomness. So remember, entropy will continue to increase until enough dark energy is created to rip the universe as we know it to shreds. Have a nice day.